we can take m equal to 1. Then m equal to 1 to get here C3. When m equal to 1 we get here 1. 1 plus 2 is 3 and C 1 plus 1 is 2 minus m equal to 1, that gives me 0. So I get here this is equal to C3. C2 is equal to C0 by 2 and we get here C0 by 2. I get here C0 by 2 into 1 by 3, we can C0 by 6. That is the value of C3. When I take m equal to 2, then we get here C4. We get 2 over 2 plus 2 is 4. C2 plus 1 is 3. And we get here this is 2 is 1. 4 into 3, this is 1 over 12, C0. I put the value of C3 and C2 here. The value of C3 and C2 simplify, I get C0 by 24. Then I take m equal to 3. When I take m equal to 3, we get here C5. We get 3 over 5. And 3 plus 1 is 4. We get 3 over 5, C4. And m equal to 3, we get here 2. M equal to 3, we get here 5. We get here 4, C2. So we get here 2 over 5 into 4, C2. Here cancel, we get 1 upon 10. So we get 1 upon C. We'll put the value of C4. And the value of C4 we substitute it here. That is here is C0 by 24. And here 1 upon 6. We simplify this one. We get here C0 over 120. Now we take our series about x equal to 0 and substitute the values of C3, C4, C5, C2, C3, C4, 5 in terms of C0 and C1. As we said, this is our second order differential equation. We can get two arbitrary constants. So we substitute our values of C2, C3, C4, C5 in terms of C0 in this equation. We're having the first term C0 and plus C1 of x. Then these are in terms of C0, C0 by 2, C0 by 6, C0 by 2, 24, 120. And then we take here C1 of x is this term out, and then this C0 out. We get here 1. And then we having here plus x squared by 2, x3 by 6, x4 by 24, and so on. This is my general solution. Now we want to find the value of C1 and C0. We are given here, this is my value of y. If we get here value of y. And now we need here the value of y at point x equal to 0, y dash. I find here y dash from this equation. When we differentiate this one, I get here, first I apply this one to get the value of constant at x equal to 0. At x equal to 0, we have y is equal to 2. When substitute in this equation, x equal to 0, then these all are equal to 0, and we get here C0. This implies C0 is equal to 2, because we are having here the y at point x equal to 0. This is equal to C0, but this is equal to 2. Now we need to find y dash. We differentiate that one, and we get here value of y dash. Differentiating this one, this will be 0. We get here C1. Plus 2C2 becomes C0x. And then we are having here C3, we get here C0 by 2, x squared. Then plus we are having here, differentiating this one, we get here 24, we get here C0 by 6, x to power 3, 0 by 6, x to power, here x to power 2, x power 3, and so on. Now I use my second condition. We have used here our first condition. Our second condition is when x equal to 0, y dash is equal to y dash of 0 is equal to 6. Now we substitute this one. When we take x equal to 0, these all are equal to 0, and we get here C1 is equal to 6. That's the value when we get here. Now we have the value of C0 and C1. I substitute the values of this constant, arbitrary constant in my equation. I get the particular solution. So my particular solution is y is equal to, put the value of C1 is equal to 6. We get here 6x. Then value of C0 is equal to 2. So we get 2, and then we are having inside 1 plus x squared by 2 plus x cubed by 6, and plus so on. So this is my particular solution, a solution of my initial value problem. Because when we have the initial value problem, we get the particular solution. This is initial value problem. This implies we're going to get here particular solution. In case we don't have the initial condition, then we get here general solution. We get the general solution in step 1. Here we get the general solution, and then we use our conditions. That's our initial conditions. These are our initial conditions. And using these initial conditions, we find the values of the arbitrary constants. The arbitrary constants are C0 and C1 and C0, and we can find the solution. So this is the idea that we can solve the initial value problem with the help of the power series. Step 1 is we find the solution, the general solution, and then we apply it, we get the particular solution. I'm going to give you a new example, and here we are going to take non-homogeneous differential equation. Homogeneous differential equation is y equal to 0, the solution of that one, and we say each terms contain y. Here we have the right hand side which does not contain y, then we say it's non-homogeneous differential equation. Till now what we have discussed the homogeneous differential equation. It's not difficult, it's very easy, and just we are having here this equation y double dash minus 4xy dash plus 4y is equal to e to power x. To do this term, we say this is non-homogeneous. Now we look on this one, our coefficient here is 1, so x equal to 0 is the ordinary point. When x equal to 0 is the ordinary point, we define our power series about x equal to 0 and its derivative about x equal to 0. Now also we define our right hand side the function e to power x in terms of about x equal to 0. We have already, I have given you the introduction of this one. This is the Maclaurin series. If it is at x equal to 0, if other than 0, then we say that's the Taylor series. So it's 0, so Maclaurin series where n is from 0 to infinity to x to power n. So we substitute the values for y and value for e to power x in terms of series about x equal to 0. So we put the value y double dash minus 4x y dash minus 4y is equal to e to power x. Now as I told you, we always take this x inside, multiply by this one, so we get x to power n, so we say n is equal to m. Here is n minus 2 is equal to m, and here again n is equal to m, and only here is the change, there is no change in the rest of the equation. So this we know that here m is equal to n, so we say n is equal to m plus 2 and replace every m by m plus 2. So we get here, this is when n is equal to 2, then m is equal to 0, when n is going to infinity, m is going to infinity. And here we get here m minus plus 2 and m plus 1 c, here n change to m plus 2 x to power m. So here there is no, in all of this one there is no change, only we change m by n by m. So now we are having here the powers are same. We want to equate the summation. When we want to look on the summation, then this m equal to 0, this m equal to 0, and this we are having here m is equal to 0. So we take here m equal to 0 out. When we take m equal to 0 out, then we are having here from this term and this term, we get here m equal to 0 is 2 into 1 is 2, m equal to 0 is c2, x to power 0 is 1. From here we get m equal to 0 out, c0, x to power 0 is 1, we get minus 4c. On the right hand side we take m equal to 0 out, and we get x to power 0, where 0 factorial is 1, 1 upon 1 is equal to 1. Remember this one, we have to get 0 factorial, that's equal to 1. So get 1 upon 1, this is equal to 1, and then the rest is coming from 1 to infinity. Now we can equate the power of x from both the sides. This is the power of x when x equal to 0. X equal to 0, we having 2c2 plus 4c, 2c2 plus minus 4c, 0 is equal to 1. Here this is equal to 1 on the right hand side. In the last of the example, whole of the examples before, we have in homogeneous and the right hand side is always 0. Here now in this case right hand side is not equal to 0, is having the value. So when we take the powers of m, so this one m plus 2 into m plus 1 c2, and the minus 4 common, we get m plus 1 cm, and here we having cm is missing, we write here cm, also here I write cm. So we get here and 1 upon m factorial x to power cm. So this is the when we equate, now same way of taking out this whole coefficient is equal to this coefficient of x to power m, and we having this equation. Now we always take this subscript, bigger one on the right hand side, other on the left hand side. We are having here cm plus 2, the coefficient is m plus 2, m plus 1. We take this one to the right hand side, this will become plus, and it's already plus. So we divide by m plus 2, m plus 1, we have m plus 2 into m plus 1. This m plus 1 will be cancelled with m plus 1. And here we will get here, this will be equal to m plus 2. So we can write my recursion relation as c m plus 2 is equal to, we cancel this one, we get here 4 over m plus 2, and then we having plus 1 over m plus 2 factorial. This here is m plus 2 into here the value of m, cm here is cm, and here there is no cm on this one because cm is not this with the 1, and we get here this m is taking values 1, 2, 3 and so on. So we can see here the value of c2, we get here value of c2 is equal to 4c2, the 2c2 plus 1 by 2. So these are the two equations. We use it to get the values of c's and substitute in differential equation. We just substitute the values of m in this one and we get the value of c3, c4, c5. Here we get the value of c2. c2 is 2c2 plus 1 upon 2, that's 1 upon 2 factorial plus 2c2. When I take here c m equal to 1, I get here 1 over 3 factorial plus 4, and 1 plus 2 is 3 into c1. When I take m equal to 2, I get here c4. I get 1 over 2 plus 2 is 4 factorial, and we get here 4 over 2 plus 2 is 4 c2. Then this is cancelled, and we get equal to 1 and put the value of c2. Value of c2 is 1 upon 2 factorial plus 2 c2. Substitute here 1 upon 2 into 1 upon 4, that is equal to 13 upon 4 factorial plus 2 c0. Now we can have n equal to 3. When I take n equal to 3, 1 over 3 plus 2 is 5 factorial plus 4 over 3 plus 2 is 5 c3. And then we are having here c3. The value of c3 we have to calculate here. This is 1 upon 3 factorial plus 4 upon 3 c1. Substitute the value here, simplify, get 17 upon 5 factorial. And then we have plus 16 upon 15 plus c1. So this is the values I get by simplifying this one. And we substitute these values in our series. Y equal to sigma n is from 0 to infinity c n x n. I expand this one, I get c0 plus c1x plus c2x square, c3x cube, c4x power 4, c5. I have these values, and we have the values in terms of two variables, c0 and c1. Because we are having here second order differential equation, we can get two arbitrary constants. So I substitute the value of c2 here, value of c3 here, this value of c3, and value of c3, and value of c4 here, and so on. We can expand it, we can get more terms. Then I equate the terms with c0 together is 1, and here we get here with c0 is 2 cx square. Then with c0 we are having 2 cx to power 4. So we are having these values for c0. This is not here c4. We have substitute the values of that one in terms of c0, and then we are having now values for c1. C1 is here is x. Then for c1 we are having a 4 by 3x to power 4, and will be termed with c5. Then we are having the values which is coming without c0 and c1 is 1 upon 2 factorial x square, and 1 upon 3 factorial x cube, and 13 upon 4 factorial x to power 5. Now you can see it here. This is my y1, and this is my y2, and this is my yp. So you can say y equal to c0 y1 plus c1 y2. We know then whenever we are having the homogeneous non-homogeneous equation, we have yc and we are having yp. So this is my yc, c0 y1, and c1 y2 and yp. So this was the idea that when having non-homogeneous differential equation, we can apply even our power series method to solve a problem. So this was my last example for this purpose.